So poor, so poor. Wait, what? Oh, parkour. Okay. It's so laggy. Oh god. Oh.
Good afternoon, everyone. Hello. Hey, could you please mute yourself so we can start with the lesson? Yes, and we're gonna do grade 12 physics today. So all of you will have an incredible headache after today. But I have videos in it as well, so hopefully you can understand it a little bit. Today we are gonna talk about quantum mechanics. Maybe,
I know that.
yeah, I'll try to explain. Yeah, please mute yourself. Maybe you know that all of us are made out of molecules. If we cut ourselves into smaller and smaller pieces, we will get molecules like oxygen, hydrogen, water is a molecule as well. Now, some of these molecules we can even chop them up even smaller. This is what we call quantum mechanics. So today we will look at our world in the smallest way possible. Okay? Now, don't worry if you don't understand. I know it's really hard. Yeah? No stress. So, today, quantum mechanics. We are just scratching the surface. Now, why do I say this? We, as physicists, people who study physics and science, we have only studied this for a short while, only 120, 130 years. So we actually don't know much yet about all of this. And every year, new discoveries are being made. So the things that we learn here at school are already old. But we cannot make a new book every year. That would be costly. It would cost the school a lot of money. So we try to teach you things in a really simple way. So today I will try to teach you how things work in a in a really simple way. And for the ones who are on the internet and try to look for the ones, I have more difficult stuff for you as well. So let's start. What will we discuss today? We will take a look at what is quantum mechanics. I will explain what it means. We will look at the history of quantum mechanics, the history of the tiny particles. We will take a look at what we can do with quantum mechanics and the future of technology with quantum mechanics. Now, here we go. Really hard piece of text, don't worry, I'll explain it directly. The branch of mechanics that deals with mathematical description of the motion and interaction of subatomic particles. What is this, Pacquiao? Now, what we mean with this is, in quantum mechanics, we look how the tiniest pieces in our universe interact with each other, how they work together or even work against each other. Some of them work really well together and they give us something that we call energy, like an atomic bomb. It gives us a lot of energy. We can blow up an entire city with it, or we can make electricity with it and use it in a peaceful way. Incorporating the concepts of quantization, we are looking at how much energy something can give us. If something is really small, it interacts with the world in a different way. Look at a tree. If we have a tree and we try to put it on fire with a matchstick, it doesn't work because the tree is too big. If we make the tree into small pieces, let's say we chop it up into sawdust, and you try to put the sawdust on fire, you will see that this interacts really well with fire. The reason is because things work differently if they have a different size. I am really tall. It's handy when I want to pick up things at a certain spot. But for me to pick things up from the ground is really hard because I'm so tall. For all of you, because you're students, you're not so big. You can easily pick up things. For me to jump and make a salto, make a turn in the air is really hard because I'm really big. For younger students, it's really easy to turn around in the air. So we look at how this works. We will look at wave particle duality. And what this means is that everything that we see around us is just an average of what we see. Actually, the whole universe is changing, but our mind, it cannot see all these changes so quickly. So our mind makes an average of everything. It just blurs it a little bit so we don't get a headache when we look. I can be here, but I can actually be in New York at the same time. But because this is really improbable, my mind cannot make this thing up.
I
But
don't understand.
you should be able to do that. We will look at the uncertainty principle. Now, what does this mean? Everything around you actually doesn't need to be there. It's just an imagination. We get photons, light into our eyes, and with this we imagine the world around us. But for me, red is red. Maybe you see red as green. But you think it's red because you're used to it. And we look at correspondence interacting with each other. Look at our body. We are made out of many molecules, but we stuck together. How do these molecules know how to work together? Which molecule says to my hand, you need to move, or my nail to grow? Does this work? We'll take a small look at this as well. So, what does it mean? Quantum mechanics describes how the universe works at the smallest level. Quantum mechanics is the part of physics that describes how the particles that make up atoms work. You might know if you're in grade 7 or in grade 8 that you have electrons, protons, and neutrons. But actually, this is already old. The proton is already gone, and we use something else for it. Now, quantum mechanics also tells us how electromagnetic waves, light or radiation, works. So we're gonna take a small look at what light actually does. What is light? And where does light come from? Is it just a star or a lamp which gives us light? Or is it something else? Okay, everyone already a headache? Okay, oh, that's too quickly. Heck, the other way. I double click. Now, heard of atomic and subatomic particles. Now, an atomic particle are all the elements we have. Maybe you've ever seen this big chart in our chemistry lab with iron, nickel, hydrogen, carbon, oxygen, lithium. These are all elements. We call these atoms. Now, if we can look at the atom, let's take the next page. We can look at the atom as a ball. On the outside is the electron cloud, which interacts with everything. And you can see the electron cloud as big as our school. And on the inside, in the nucleus in the middle, we have the protons and the neutrons. And you might see these in comparison with our school like the smallest tip of your pencil. So actually, most of the things around us is empty space. 99.99999% of everything in the universe is actually nothing. There is nothing there. Then why can I touch something? Why can I feel something? Now, this has to do with electricity. The electrons on the outside together they make an electric field. Maybe you've ever felt this when you played with magnets. If you put the magnets close together, they might smack into each other, or they have a little bit of a force field. You cannot get them close to each other easily. Now, this works exactly the same with atoms. These electron cloud, this part of electricity, makes a little bit of a bubble, and these bubbles touch each other. But actually, it's not the bubbles which touch each other, it's the electrical field which makes it. So when you put two magnets together and you put minus against minus, you can feel that they resist. They cannot touch each other. Now, you cannot see anything there, and it works exactly the same as the electron cloud. You cannot see that there is something there, but it's still touching each other. Now, let's go back to the previous page. Subatomic particles are small, the smallest things you can imagine. So if we have a molecule, we are made out of molecules, and you chop this into pieces, you get the elements. And if you get these elements, they are also cut into smaller pieces. So what do we learn here at school until grade 10 are protons, electrons, and neutrons. It's the things you see in the atomic model. The proton, which is positive, and the neutron, which is neutral, they are in the middle, in the nucleus, and they make up what we call mass, weight. They are the things which are heavy. The electrons on the outside weigh just one out of 2,000 of a proton or a neutron. So if we have 2,000 electrons, they weigh just as much as a proton. Now, different weights and different amounts of proton, electrons, and neutrons make up the different elements we have in the world. Hydrogen, where our star is made from, has the fewest subatomic particles. Hydrogen gets compressed. Two hydrogens come close to each other and closer, and all of a sudden they fuse together. Now, this is what happens in our star, in the sun. These elements come together and they make a new element, helium. So helium is actually two hydrogens fused together. If we can fuse them a couple of times more, we can get oxygen or even carbon. If we fuse them a lot of times, we can get things like uranium, which we use for our nuclear power plants. Now, the bigger these fusions are, the more subatomic particles there are, the more unstable it gets. So the heavier something is, the more particles inside, it means it also decays more easily. So things like uranium and plutonium, which are really heavy, they also decay. This decay is what we call radiation. So if you have a chunk of uranium and you keep it in your hand for a while, you might notice that your hair will fall out and you will get sick and eventually you will die. Now, what actually happens here that this element is unstable. And these super tiny particles, the proton, the electron, and the neutron, are flying away and they go straight to your body. They damage everything which is inside you. So you get sick. We call this radiation poisoning. Now, nowadays, we use this in a different way as well. Let's say someone has cancer and this person is sick, but the cancer is in the middle of our brain and we cannot do an operation. So, what do? We send these rays, these particles, into the brain. It will damage many stuff. It also kills the cancer cells. Someone who gets a treatment with radioactive material, they get radiated, they lose all their hairs, and all their cells will die, but the cancer cells will die as well. And hopefully, they will be cured. Now, if we're going to look at a more advanced model, this is for grade 11 and 12. Now, I didn't see any of the students of grade 11 and 12 here. You might learn that the proton has been taken away. The proton is changed with quarks, leptons, and gauge bosons. And of course, the Higgs boson particle. Now, the Higgs boson particle, I didn't write it down because this actually keeps all the elements together. It's what we see as the fundamental part of gravity. Now, quarks are the type of flavors which a subatomic particle can have. You might ask me, flavor, what do we mean with this? It's the feeling it will get you. We have up and down, which are opposite to each other, bottom and top, which are also opposite to each other, and strange and sharp. You can look at these as type of dimensions inside of quarks. Now, leptons, we can see these as more charged particles. Together, they make up the atoms. The quarks do not actually make up atoms, they don't have a lot of weight. Now, the leptons make up the weight, and especially the muons and the taus, they make up the weight inside of your atom. So we have the electron and the electron neutrino. They are on the outside of a cloud, and an electron neutrino can be seen as an antiparticle. We have the muon and the tau. Together, they make your proton. And these are opposite to the muon neutrino and the tau neutrino. Now you can see these things as antimatter again. And what happens when matter and antimatter, like a muon and a muon neutrino, heat each other? They create what we call photon. This is a reaction, and this is what we see in light. So actually, what does this mean? Everything that you see is a reaction of two particles which are opposite to each other, and they hit each other. So actually what we see has been nullified and it's not there. And everything that we touch, we put something on it, we cannot see it anymore, and all of a sudden you notice that there is matter. But everything which gives us light is actually not there. But this is for grade 11 and 12, so for the younger kids, just erase it from your mind and hopefully you'll understand this in 10 years. And the Gauss boson is the photon of electromagnetism. It's the reaction between matter and antimatter. We have the 3 W and Z bosons of the weak forces and the 8 gluons of the strong forces. Now, what does this mean? Gauss boson is the 4 fundamental parts of new physics. It's electromagnetism, which we can see as light and particles attracting to each other. The weak forces and the strong forces, these are interacting inside of an atom. And we have, of course, the last and fundamental force, which is still gravity. Okay, woo, how they go. Now, here we can see the atomic model. A long while ago, 2,000, maybe 3,000 years ago, the Greek already looked at things like we can make things smaller, smaller, and smaller. And at a certain moment, we cannot make it smaller anymore. So they call the smallest thing in the universe atoma. And from this, we still have the name atom. It comes from the Greek philosophy. philosophers like Plato studied this. And he thought about this what would happen if we make it smaller, smaller, and smaller. Now, a short history of quantum mechanics. You might learn this already in grade 7 and 8. Now, before the First World War, we already started to work on the theory of physics of the great scientist Isaac Newton. But the more and more we studied things, we saw that things interacted differently with each other. So we started to look at more things. Maybe we could discover more things. Now, looking at the electron, which is on the outside, it's not the same as electricity. Now, the symbol for electron is E minus, and it has a negative charge. This theory has been developed by Sir Johnson Stoney already in 1874. There weren't even cars yet. Can you imagine that? We already know, actually, we already can make an atomic bomb with this, but we didn't even know how to make a car yet. So, this is how far we already were with physics at the time. People were really smart at the time. Now, later on, people researched it more, and the one who discovered this is J.J. Thomson in 1897. Thomson got a Nobel Prize for physics for this. Now, if we look at the neutron is the particle which has a weight, but it actually doesn't do much. It has no electrical quantity, but it still interacts with everything. So you can see this as a bit of glue in the middle of our atom. The symbol for the neutron is the letter N, and the theory has been invented by Ernest Rutherford. It's a man from New Zealand, and in 1918 he theorized that there could be something else. We only thought of electrons and protons, plus and minus, but he thought there should be something else because the calculations they don't measure up. We are missing a little bit of weight. So he theorized that there could be a neutron. Now, this one has been found by James Chadwick. Now, both Rutherford and Chadwick got a Nobel Prize for what they discovered. Let's take a look at the proton. Now, the proton has been thought of by many, many, many people, and we cannot actually give a credit for this to anyone because millions and millions of people already got so far. Like there is a negative, so there needs to be a positive. If you jump up into the sky, you will fall down again. And people already saw that there was more than life to this. One found. Now, how did he follow experiment? And he actually sent particles to a little bit of iron, to a little bit of gold foil, and they hit each other and they started to move with each other. So he knew there was something else in here. There's positive and negative, like a magnet. They interacted with each other. So this is what he found out, and we still study this in grade 10. You need to learn this, and in grade 9 probably as well. Now, then there is something which we call antiparticles. Antiparticles are the opposite of what we have right now. The electron will be positive, it's completely the opposite, and it will have a weight. The neutron will have no weight, just as the proton, and they also have a different charge again. Now, this theory has been invented by Paul Dirac. Paul Dirac has been voted as the second best physics person in England. First will be Isaac Newton, but Paul Dirac also did a lot of research. And he challenged Einstein with his theory of relativity. So we had Paul Dirac and Niels Bohr and a couple of other scientists, and together they looked at Einstein and they saw Einstein might be wrong. Einstein is also right on many things, but other things Einstein was completely wrong. Now, the photon, which we call light nowadays, is the symbol Y or the gamma symbol. This theory has been theorized by Max Planck and Albert Einstein. Now, Albert Einstein, of course, you know this man with the weird hair, big glasses, the inventor of the atomic bomb. Not that he wanted it, but he helped a lot with the research. Now, Max Planck, if you are in grade 11 and 12, you will hear his name quite often. He has an institute named after him, and also the highest temperature possible to be reached by a certain element. It's what we call the Planck temperature. So he has more things in physics named after him. But there's almost nothing named after Albert Einstein. The theory of relativity, E is mc squared. That's the only thing, and he has an element, Einsteinium. Now, this has been discovered by Ernest Rutherford and found gamma radiation. Now, what does this mean? He could see that if things are not stable anymore, they lose weight. They become less, less. Actually, dissolve. What they do not beta and alpha particles are really small. We can see the heat. Beta particles already consist out of atoms, out of particles. It is actually smashing straight through us. That's what we call light. Now, the neutrino is the opposite of the neutron. V theory was by Wolfgang Pauli and Enrico Fermi actually as well, but Mr. Pauli was earlier. We just didn't read his books yet. This has been described better. I didn't write down Enrico Fermi, but Enrico Fermi is also the man who theorized like, are we the only one in the universe? And where is everyone? And what does everyone do? And he also had this theory that if we have an explosion, it goes up and also goes down. We call this the Fermi bubble. You can see this if you take a picture of a universe, of a different galaxy, and you can see two bubbles, one on the top and one on the bottom, with radiation. And this means that two things were working opposite to each other. Now, enough of the history. This is far too much for the younger kids. Now, what can we do with quantum mechanics? If we speak in a wide range, quantum mechanics incorporates four classes of phenomena, for which classical physics, the speed and mass, that doesn't work with this anymore, so we do not work with this. So they have the quantization of certain physical properties, energy, quantum entanglement. This means nothing else that things are interacting with each other. The principle of uncertainty. Is it what I see actually there? And the wave particle duality. Now, I'm going to talk a little bit about wave particle duality. If we send a certain single subatomic particle only once somewhere, sometimes we can measure it at two places at the same time. So, is the particle actually there? The answer is yes and no. Yes, it is there because it's actually everywhere in the universe at the same time. And no, because mass cannot be in more places at the same time. But how does this work, Payal? How can you explain this? Now, what we see around is just some average of which is there. And from everything that we measure the average. So it's never completely certain. We take things for granted. If you flip a coin a million times and it lands on its side only once, is it head or tail? Or was it something completely different? Because a coin can land on head or tail, but we didn't take in the equation that the coin can also land on its side. And it's neither head nor tail. Now, what do we do? Is we make semiconductor electronics. Now, what does this mean? We have our microchips in our computers. And at certain levels of tallness, of mass, and electrical quantities, they can react in two ways at the same time. So instead of you being able to cook dinner and to cook another dinner in a different pan, now you can cook both dinners in the same pan. Because you can have 0 and 1. You can have yes and no at the same time. And this makes things a lot quicker. Now we use it for lasers to send certain photons, beams of light. Atomic clocks, we look at time more precisely, and we know that carbon degrades at exactly 1.6 billion years old. That's when our sun came to life. We can look at magnetic resonance scanners. This is nothing else than your printers and your scanners. It is a light reacting with something, and we get a electrical response. And this electrical response, we see it as we scan a certain color. So we hit something with light, the light comes back, and something responds with this. And this is how we can copy and print certain things. So it actually looks at things like light and matter. Now, for the younger kids, I made a cool video. Actually, I didn't make it, I just downloaded it. But I'll show you a short video which shows how things work with a little bit of animation in it.
Quantum physics is a mystique of being complicated and hard to understand. In fact, Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, said, if you think you understand quantum physics, you don't understand quantum physics.
Which, now, what does he mean with this? It's the uncertainty property. Whatever you see might actually not be there. When you think that you do something, you might actually not do this at all. Everything is uncertain.
Which is kind of disheartening for us because if he didn't understand it, what chance do the rest of us have? Fortunately, this quote is a little misleading. We do, in fact, understand quantum physics really well. In fact, it's arguably the most successful scientific theory out there and has let us invent technologies like computers, digital cameras, LED screens, lasers, nuclear.
Oh, I didn't want to do that. Sorry, yeah?
That's the very. You know?
Okay. Now, quantum mechanics, what do we do with this? As I told before, cameras, they also work with light. Light emitting diodes is what you see inside a computer, all these flashy lights. They see certain things and they interact with things. Lasers is what we use for a laser pen, and nuclear power, of course, is the thing for energy and for atomic bombs.
So you don't really want to build a nuclear power plant if you don't really understand how it works. So quantum physics is the part of physics that describes the very smallest things in our universe.
Now, here on the left side, you see the molecules, the smallest things in our universe that we could think of. But these molecules are made out of these little bubbles. And these bubbles are actually your elements. So let's say here we have H2O, water, one big hydrogen, and two small oxygen. Oxygen and hydrogen are the elements, and we can take them apart from each other, and we can even see smaller things. The atomic physics goes to subatomic physics. And we have this model of the atom, and inside the atom are even smaller particles. So we have the molecules, the atoms, the protons, the neutrons, and the electrons. And for grade 11 and 12, we even go in deeper. Let's go a little bit further. So, actually, what we try to understand in this is that everything in the universe works in a certain wave. Everything works in a type of vibrations. And if you vibrate two things together, they make something else. Like I'm shaking and it makes me warm. But if we have, for example, sound, We have one sound from a piano and another sound of a piano, and together they make a new tune. Instead of two single tunes, you will hear one tune. Let's take a little bit further at this. Now, here is what we saw with the double slit experiment. We shoot electrons through a hole, but it can actually be at two places at the same time. And we see what you see here in the picture. This is a wave pattern. Where there are many dots, it's the top of the wave. And where there are no dots, it's the bottom or the trough of the wave. So if we would put this on its side, and we make a bubble where green is, and we make a hole where white is, you might see that this works as a wave as well. Now, how does this happen? If things go through a hole, they can go to more places at the same time. So what do we see here is the wave pattern, and we think that everything in the universe might be a wave. But as we just studied physics, it might be something completely else as well. We are just starting to scratch the surface. We are just starting to see what is what. Now, what does this mean, these waves? Where there is a high point, that means there's a high probability. It has a big chance. And if there is a low point, there's a very low probability. But this very low probability is not zero, and it will never be zero. So actually, I can turn into a tiger all of a sudden. But the probability is really, really, really low. So probably it will never ever happen in our entire life. But it can happen. Now, what you see here is what we call superposition. This is what Jerome is good at our school. Jerome plays the piano. If you combine two certain tones at the same time, they make a nice tone together. We call it a chord. If they do not combine nicely with each other, they work against each other and it sounds false in our ears. It's the same as when you hear me singing. I'm really bad at singing, and this position will not be nicely. So you think like, it hurts my ears, Pagello. And I say, yeah, you just shouldn't let me sing. Now, the entanglement shows that when two waves work together with each other, they might get rid of each other. So two waves hit each other, it's like sound hitting sound, and all of a sudden, together they make a chord, and they are stuck together. They work together, and they work together quite fine. The reason why is because they look alike. Now, actually, it is completely the opposite from each other. Light will be dark, up will be down, and bottom will be top. So this is a problem. Now, what Einstein said, can there be anything faster than light? Now, Einstein's theory says no. The reason is if you want to be faster than light, that means you need to have more energy than light. And if you go quicker, that means you become heavier. And if you go faster than light, that means you should be heavier than the rest of the universe together, which stops you directly because you are too heavy. Now, this can be seen in a different way as well. Let's say I move really quickly to the left. From here, I move to the middle, I move to the left, and something from the other side also moves, but then from the right. Both of us are almost at the speed of light. That means we come together at a speed which is Now let's look a little bit further. No, this is too hard for all of us. Let's take this away. So, what they look at things is, can things be at different places at the same time? How does this work? Now, for this, I will use matter. We do not look at a single moment. We look at millions and millions and millions possibilities at the same time. Now, from all those possibilities, almost all of them are. That's what we see around us. And there is this small part which could be different, but we will never notice it because it's so small and so short. Now, the future of technology, what kind of things can we expect in the future with quantum mechanics? It's nice. Now, first of all, is quantum computers. If we have a computer and we make the parts of the computer even smaller, that means we can do more things at the same time. We can say that things are zero and one, but because they are a semiconductor, instead we say yes and no, we can say yes and no at the same time. So things can work twice as quickly. Now we call these quantum bits. We're still working with this. Don't worry about it. I will not ask questions about this. Now we are developing these quantum computers. The big problem is they need to be super, 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 super cold to work. So on Earth, it's really hard to make them work. But in space, where it's super, super cold, they can work really well. Now, what can we do as well is a nanotechnology. Nanotechnology is not looking at the quantum technology right now, but it's still a little bit bigger. We can make certain things inside of a carbon grid. Now, this carbon can work as a semiconductor. It can do two things at the same time. So we can let something be green and yellow at the same time. We can let things do more than one thing at the same time. Now, how do we want to use this? Let's say we have a stone. We give this stone a little bit of electrical impulse, and this stone will act like water. It is still a stone, but it will become liquid. We take this stone in a bucket and we put it somewhere else. We give the same electrical impulse again, and all of a sudden it will be hard. So things we can work with things quicker. Now, nanotechnology doesn't mean anything else than things are really, really, really small. Really small. So we can make all robots of this. We can make things work inside of our body. Now, here as well is what we can use in medicine. We can send a certain nanobot. They can do certain stuff. They don't look like this, by the way. But they do certain stuff and they recognize certain cells and they can fight against these cells. For example, cancer cells. And they will only kill the cancer cells. Beautiful, nice screen here. Now, other things that we can look at is how structures work. Nowadays, we use bolts to turn. If you look at your door, it has a couple of bolts. But what if we can let something move in its own structure? Instead of having all kind of materials, the structure can change by itself. Making the structure stronger or weaker at a certain point can make things move. Like half of the thing can bend and half of it cannot bend. Let's give an example for a door. If you open the door, it opens the entire door. But what if the door could look at you and you only push open the part of the door where you will walk through? It will use less energy for you. Now, capacitors are nothing else than things where we can store our electricity in. You can see these better and better. Now we can make cars out of these and that kind of stuff. Stronger batteries mean stronger cars. Artificial intelligence are chips which can think by themselves. Actually, we don't want this because the robot is much smarter than us and it will make more robots and it will take over the world probably. But still, we can let a robot think for itself, and the robot can adapt to certain things, just as we. If we eat something and it's really hard, we will not chew really hard because it will break our teeth. We will wait a while until it's soft, or we can chop it into smaller pieces. Now, if a computer can adapt as well, it makes a computer much smarter. Now, artificial robots, we call them androids. Maybe in 200 years, they will walk the world. VR immersion, you might have seen VR sets already. The weird glasses you can have on you, and you can make it more real. Now, when we touch certain things, we don't feel them. But then, actually, because of the small electrical impulses, we can feel everything just as we would feel it normally. And VR, the virtual reality world, would become really real. We could feel pain through a machine. We cannot even see things, we can feel the wind.
Semua dijadiin
Sharp.
satu, seribu, dua
And
ribu
we can
sama
live in
100.
a
Pokoknya sama-sama 100, 100.
and this might be nice for the entertainment industry. High temperature superconductivity. With this, we can make things float. We already use this with magnetic trains. We can let things float and they will go to a different place. Now, this is nice because we can actually fight gravity and maybe we can make everything a lot easier. Now, gravity pulls us to the ground and it takes a lot of our energy. What if let's say I am 80 kilograms. What if I have something inside me that makes me 2 kilograms? All of a sudden, everything that I do in life takes less energy. That means I don't need a lot of food anymore and I don't get tired. So I can do much more things on a day. Now, here we look at superconductivity, what it actually does, what we can make out of it, and it will make what you see here the Durax belt. They do not react with each other. What do we do with these? Like the magnetic trains, we can let things float on top of actually air. The problem is these things are quite expensive. Because really quickly, let's say you sit in a train and you crash into a wall. The normal train doesn't go that quickly, but if you have a train which goes 4 times as quickly and you have an accident, this is quite dangerous. Let's say someone fools around with your rails, throws a piece of iron on it, the magneticity will come, will become. Now, the last thing that I wanted to show to you is fusion power. Now, nowadays we only have fusion. The energy of particles is falling apart. And And with fusion, we want to do something which puts some particles together. Okay. Okay, here we go. Turn this one off. So, are there any questions for today? I think a lot, because all of you in the younger classes. Is there anything? Anyone for a question for today? Or are all of you having a big headache right now? Like, oh my God, Pa Jelmer, what was that? Let's take a look at the chat, okay? Oh, sorry, I didn't see all of your messages because I was.
Banyak sekali juga ibunya.
Pa Jelmer is our, oh, hello Eve, if you're still here. Pa Jelmer is our sun's inner core made out of helium. Now, inside the core of our sun, we have a hydrogen which fuses into helium. So we have both hydrogen, helium. We also have heavier elements like oxygen, carbon, and irons. Did Einstein win against Paul Rudder, Pa Jelmer, in physics? No. Quite simple, there is no winner in physics. We try to invent new things, and people in, let's say, 500 years ago, they didn't know everything that we know right now. It doesn't make these people stupid or wrong, but they were just not so far as we are right now. So the people who study physics right now have a more of a background. They have other people who already did a lot of work for them. So it doesn't make someone wrong or right. It's just their point of view at that time in life. Like 2000 years ago, if there was a comet in the sky, we would be like, oh my God, it's the end of the world. That doesn't mean that they're wrong. If the comet would have hit us, it would have been the end of the world. But now we know the orbit of a comet. We can see what it does. We can actually see where it's made from for the light that it makes. So Einstein was not wrong. Einstein didn't know better at the time. Okay. Oh, the screen sharing went away. I cannot see that when I'm sharing screen. I'm sorry. Okay, is there anyone else with a question? Eve, do you have any questions? You're in grade 10. We do physics like this next year. Do you have any questions for me, Eve? Eve is hiding behind his desk now. No questions. No. Eve, if you join grade 11 and 12, we will look more into the things like antimatter and matter and the collision of particles. And in grade 10, you will see things like radiation. We will go into them a little bit. Last year, I didn't have much time to explain everything because of a different schedule. This year, I will have a lot more time, so we can go a little bit deeper into this. So you have a couple of lessons like this year. And yeah, good luck on my lessons. I really like this part. So for you, Eve, you look at the elementary particles, protons, neutrons, electrons, and in later years, in grade 12, we will go more into quarks and leptons and that kind of thing. We look at what is actually inside of the element. Nowadays, we explain this standard model because it's easier for kids to understand, but it's actually way and way deeper. It has more dimensions to each other, and things don't only interact because of electricity, but because of other things as well. They don't like each other in that way. Anyone else with a question? Gio, do you have more questions? Do we have to wear sunglasses when there is... Yes, Now, you have two types of sunglasses, Gio. You have sunglasses which just blind the light, and you have sunglasses which block UV light. It's a type of a sunscreen. Now, ultraviolet radiation, these are really short beams, really short waves. And when they come into your eyes, they will damage your cells a little bit. If we look at the other pieces of light, these waves are a lot bigger. They are huge in comparison to UV, and they don't hit many cells inside of your eyes. So UV radiation, Röntgen radiation, alpha, beta, and gamma radiation, these are the most tiniest things. You can look at this as I stab you with a pencil. Yeah, and it's a really big movement. Only one. It will only make a spot in your belly, and you will say, "Ow, Mr. Yelmer just stabbed me with a pencil." But if we look at ultraviolet radiation, this vibrates at a really quick speed, with really short, quick speeds. Can you imagine I stick the pencil into you, but now moving it really quickly, it will do a lot more damage to you. This is the same what ultraviolet does to our skin. It damages our skin. We will get blisters, we will become red. So that's the reason why we need to use protection for ultraviolet rays. You have these from the sun, but also when you're welding. When you weld two iron pieces together, there is this super bright light, and inside of this light is also ultraviolet light. So we have special glasses, otherwise we have a headache at the end of the night. You can't even close your eyes anymore. Any other questions? And there is UV radiation all day long, by the way. The sun hits us with UV, but normally we don't really look into the sun because we know that it hurts our eyes. So if you look into the sun and you have UV glasses, it filters most of the light, but not all of it. A welding glasses, which you use for welding, that's better. It's still not good because you should never look into the sun. And if you want to see the sun in a different way, yeah, like special solar eclipse glasses, yeah. If you want to see the sun in a different way, you can also use your hat. You use a magnifying glass, and you might see if you put it on a piece of paper, it might make a really small beam and burn the paper. But you can also move it away, and it makes the beam of light larger. So actually, you are magnifying the sun on a piece of paper, and you can look at the sun. When Mercury or Venus passes the sun, we can actually see it as a small spot in front of the sun in this way. If we have a semi-eclipse, like this weekend in Africa, we said there was a semi-eclipse, we can actually see half of the eclipse. If we look into the sun, it will still damage our eyes. So we can use physics, light waves spread out, to make an image of the sun on the ground. But don't use magnifying glass and look at the sun, because your eye will be gone. Okay? Yes, special solar eclipse glasses have a filter for UV. It doesn't mean that it filters everything. It is still not a good idea to look into the sun. Any other questions for today? Nobody? Okay, well, it's 4 o'clock. If you have any questions for this, you can always ask me via CH Liaison. And if you're in grade 11 and 12, you see these things. Actually, in class, I'll try to explain it a little bit differently. But now we have a lot of smaller kids with us as well. And if I explain it really hard, the kids do not understand everything. So I hope you enjoy. I hope that you know now that next to everything that we see, there are so many small things that we cannot even see. Magnets and gravity. Can you see gravity? No. It doesn't mean that it's not there. So I hope you will be more interested in physics, and hopefully I'll see you in my physics class. Have a great afternoon, everyone. See you all on Friday, I think, or Wednesday afternoon.
Thank you, sir.
Take care, be healthy, wash your hands, eat healthy, and hopefully see you soon.
Bye. Bye-bye.
Bye, everyone.
Thank you, sir.